Welcome to the fifth session of this Functions and Relations series. In this session, we will introduce and demonstrate the analytical skills in solving problems related to sets and their relations, particularly when parameters are involved. We will present 5 worked examples and show different approaches to solve the same question.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the fifth session of this Functions and Relations topic. Through this session, we are going to demonstrate the skills for analyzing and solving questions related to this topic through 5 worked examples. The first example presents 2 sets A and B. After solving the quadratic equation in set A, we find set A contains -4 and 0, 2 elements. However, in set B, the quadratic equation contains parameter A. After solving the equation using the quadratic formula method, set B has 2 elements of x sub 1 and x sub 2, where A is a parameter. Here, x sub 1 equals -a plus 1, or in parentheses, minus square root of 2 times a plus 1, or in parentheses, while x sub 2 equals -a plus 1, or in parentheses, plus square root of 2 times a plus 1, or in parentheses. Since B is a subset of set A, we make x sub 1 equals -4 and x sub 2 equals 0. So after solving the 2 simultaneous equations, the values of A are obtained and then back substituted into the quadratic equation in set B to calculate the corresponding elements. Hence, when we find A equal to -1, set B has 1 element of 0. When A equals 1, set B has 2 elements of -4 and 0. In addition, in case A is less than -1, both x sub 1 and x sub 2 are not real number. Hence, set B is a null set, which is a proper subset of set A in this case. So, in conclusion, when A equals 1 or less than or equal to -1, set B is a subset of set A. Example 2 shows 2 sets of A and B. There are 2 elements of -1 and 1 in set A. The elements in set B are the roots of a quadratic equation of x squared minus 2ax plus b equals 0. The question is to find the values of A and B, given that set A is not a real set but a subset of set A. Since the elements in set A are already given, we need to focus on the elements in set B, which are the roots of the quadratic equation. After working out its discriminant and assuming it is greater than 0, we use the quadratic formula to find the expression of x sub 1 and x sub 2 in terms of A and B. Here, x sub 1 equals A minus square root of A squared minus B, while x sub 2 equals A plus square root of A squared minus B. Since set B is a subset of set A, we set x sub 1 equals -1 and x sub 2 equals 1. Based on that, we calculate that A equals 0, B equals -1. When the discriminant equals 0, the quadratic equation of x squared minus 2ax plus b equals 0 has only one root, and it becomes x squared minus 2ax plus a squared equals 0. After solving the equation, the values of A is either -1 or 1, and the value of b is equal to 1. In conclusion, there are three pairs of solutions for a and b. When a equals 0, b equals -1. When a equals either 1 or -1, b equals 1. There are two sets of a and b in example 3. The elements in both sets satisfy their own inequalities where a is a parameter. The question is to find the value range of a given that set B is a subset of set A. The first step to approach this problem is to transfer the inequalities to their factorized form. Then we may analyze the outcome of the relation between set A and B under different value range of A. Now let's take a close look at the inequality in set A. Since its discriminant is a perfect square, then we may factorize the inequality using the cross product method. After factorizing the quadratic expression in set A, we have the factorized form of the inequality x minus 3a minus 1, or in parentheses times x minus 2, or in parentheses. At this stage, the value range of a is yet to be discussed with the inequality in set B. Here we continue work on example 3. According to the basic inequality, a squared plus 1 is always greater than or equal to 2a. Based on the inequality in set B, since it is less than 0, x must be in between the value of 2a and a squared plus 1. Now we come back and look at the inequality in set A. In order to find the critical point to discuss, we let 3a plus 1 equals 2. So the critical point of a to discuss is 1/3. Now when a is greater than 1/3, x is between 2 and 3a plus 1. Since set B is a subset of set A, the endpoints of both inequalities must be satisfied. After solving the two inequalities and then find their intersections, we find the value range of a, which is between 1 and 3, including both endpoints. When a is less than 1/3, x is between 3a plus 1 and 2. Since set B is a subset of set A, the endpoints of both sets must be restricted by the two inequalities. Hence, in set A is less than or equal to -1, while in set B, a is between -1 and 1, including both endpoints. Their intersection is just the one point of a equals -1. Therefore, in summary, in order to satisfy the requirement that set B is a subset of set A, the value range of a is between 1 and 3, including both endpoints, plus a point of a equals -1. The question in example 4 is to find the range of a function whose expression is the quotient of the sum of 2x squared and -x and 2 to the sum of x squared and x and 1. According to the function expression, we may simplify the expression and sketch the graph as shown on the screen. In the meantime, we also work out its derivative function and then set it to 0 to find the stationary points. Accordingly, when x equals -1, the function reaches its maximum. When x equals 1, the function reaches its minimum. Therefore, the range of this function is between 1 and 5, including endpoints. Here we continue work on example 4. There's another alternative approach to find the range of this function. What we do is to rearrange the function and simplify it as a quadratic equation where y is regarded as a parameter. Since the function is a value 1, the quadratic must be valid. Therefore, its discriminant must be greater than or equal to 0. Hence, we have the inequality of y plus 1 all in parentheses squared minus 4 times y minus 2 all in parentheses squared is greater than or equal to 0. After being simplified and factorized, the inequality becomes y minus 1 all in parentheses times y minus 5 or in parentheses less than or equal to 0. Hence, the range of y is between 1 and 5, including both endpoints. In example 5, as we can see, there's a function fx which equals x squared over the sum of ax and b, where both a and b are constants. The equation of fx minus x plus 12 equals 0 has two real roots of x sub 1 equals 3 and x sub 2 equals 4. There are two questions to follow. The first one is to find the algebra expression of fx, and the second one is to solve the inequality of fx, which is less than the quotient of k plus 1 or in parentheses times x minus k to 2 minus x, given that k is greater than 1. To find the algebra expression of fx, we need to find the constants of both a and b. So we substitute fx to the equation and then simplify all the terms by combining them into one fraction. Since the fraction is 0, its numerator equals 0. Hence, we substitute 3 and 4 into the equation respectively, and then establish two simultaneous equations. Now, after solving the simultaneous equations, we obtain the values of a and b, and it can be seen that a equals -1, b equals 2. Hence, fx equals x squared over the result of 2 minus x, where x is not equal to 2. This is the expression of fx. Here we continue work on example 5. To solve the inequality of fx is less than the quotient of k plus 1 or in parentheses times x minus k to the result of 2 minus x. Fx here is replaced by x squared over the result of 2 minus x. Moving the term from the right hand side to the left hand side and then combining two fractions into one. Since the numerator can be factorized as x minus k or in parentheses times x minus 1 or in parentheses, based on the factorized form of the inequality, we may find the outcome of x value range according to the value of k. As it can be seen, when k is between 1 and 2, the value range of x is the union of the set from 1 to k with another set from 2 to infinite. All the endpoints are not included. When k equals 2, the value range of x is from 1 to infinite, not including endpoints. When k is greater than 2, the value range of x is the union of the set from 1 to 2 with another set from k to infinite. All the endpoints are not included. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.